Let's look at another application of impulse momentum principle in a fluid dynamic situation with a steady flow, of course. So here we have a 90-degree elbow joint that redirects the water along a 3 centimeter diameter pipe. Knowing that water density is 1000 kilograms per cubic meter and it has an average speed of 5 meters per second, we're interested in the magnitude and direction of the force water exerts on the elbow joint. So given we have a diameter of 3 centimeters, therefore radius is 0.015 in meters. Density rho is 1000 kilograms per this is density, therefore it's 1000 kilograms per cubic meters. This is m over v, so it must have units of mass per unit volume. And let's see what else. Average velocity of the flow is 5 meters per second. We're interested in the force exerted by the water, both magnitude and direction, on the elbow joint. So without saying it explicitly, we're taking into account the fact that we have a steady flow. Therefore, as you saw before, mass flow rate is rho VA, and then I have 1000 kilograms per cubic meter times velocity of 5 times area is pi r squared, and this gives us a mass flow rate of 3.53 kilograms per second, since we were using primary units. Then if I write the impulse momentum principle for a moving fluid, it's a vector equation. It's equal to F t equal to change in linear momentum. If I divide both sides by time t, I have force F equals to m over t, or mass flow rate, times change in exit minus inlet velocity. So this is a vector equation. I want to take the x and y components of it and then do the numerical calculation. In x direction, Fx equals to mass flow rate of 3.53 times velocity of exit in x direction. Velocity of exit in x direction is 5. Velocity of inlet in x direction is 0 because inlet velocity is vertical. So this gives me some Fx, which is equal to 17.7 newtons. Then I can do the same thing in y direction. Mass flow rate is the same, that's a scalar quantity. Velocity of the exit in y direction minus velocity of the inlet in y direction. Observe that at exit, flow is horizontal, it has no y component, so that is 0. Therefore I have minus 3.53 times 5, and you see what the minus is for. The equation has a negative in front of VIY, so this gives me minus 17.7 kilonewton, newtons per, just newtons, not kilonewton. I'm using primary units of kilograms per second times meters per second. So if I draw these two components, you see I have a x component to the right and a y component down. Therefore these two add up to a force vector in this direction. This is the force exerted by the water, on the water by the elbow. Let's call it F. Reaction of this force, the force exerted by water on the elbow, is equal and opposite. And observe that I have equal x and y components. Therefore, this angle, the direction is 45 degrees. And then magnitude of the force F water equals to square root of 17.7 squared plus 17.7 squared. It turns out to be a force of 25 newtons. So this is magnitude of the force. The direction of it is 45 degrees. And observe that here we have a reaction to the force that we found earlier. So if I draw a diagram representing the, let's see, I want to draw the pipe. Well, it won't pick it up. I'm trying to use my pen. Let's try one more time. If not, then I draw it by hand. No, it won't pick it up. So let's say that this is the elbow. Force exerted by water on the elbow is going to be in this direction. Thanks for watching.